Okay, we start with chapter 6, Momentum and Collisions. This is the lecture for chapter 6, part 1. There'll be a part 2. So we're going to be talking about momentum and collisions. So let's first talk about momentum. Linear momentum is an object with mass moving at a velocity. So you have momentum, which is P is going to be equal to mass times its velocity, where P and V are both vectors. We can break those vectors up into their X and Y components, and this is how they look. Units of momentum are kilograms times meters per second. The change in velocity is equal to the change in momentum. So in this case, we could have a change in momentum, but we must also have some change in velocity. Divide both sides by time, and we get the constant net force acting on the object. So this tells us basically what the force is. There has to be some type of force, external force, internal force, that is acting on the system, and that is going to cause the change in momentum over time. And so we have this equation: the change in momentum over time is equal to the net force, or in some cases, what we call the average force. The magnitude of the momentum can be related to the kinetic energy. So if we take the momentum equation and square the equation, then we can fit it into the kinetic energy equation, and we can solve for kinetic energy and find the relationship with momentum in it. So this relationship between momentum and kinetic energy, we expect momentum to be squared, as it also relates to velocity. Let's talk a little bit about something called impulse. When a force is acted on an object for a period of time, this is known as impulse. So impulse is equal to the net force, or the average force. It could be called either one, times delta t. And we denote this not just plain t, but by the delta, to let us know that this is going to be a very small increment of time. The units of impulse are Newton seconds, and they are actually the same units as momentum, which are kilograms times meters per second. But in this case, it'd be appropriate to use Newton seconds. So here we see a force versus time graph, and during a duration, this could be milliseconds, microseconds, we have this impulse. Okay, and it's really just the amount of force that's happening in this time period. So we have a point of maximum compression. Okay, this could be you throw a ball on the ground, it compresses, and it does it for a certain amount of time. Contact begins, contact ends. This is in milliseconds, by the way. So basically, we see this, we only can actually, without using calculus, we only can actually find the average force that happens in that time frame. Back to that again here. So as it changes direction, it's going to be 0 meters per second. Okay, and then it's going to go the opposite way. It could be negative or positive depending on what you decide to use. If it's going in this direction, you could say this is negative, okay? And then it starts going in this direction after it reaches 0 meters per second. And now we're going in the opposite direction. We call this plus. So it's up to you to decide what that is. You'll be taking the absolute value anyways when you fill in the answer. Okay. Estimate the duration of the collision, the delta t, and the force, average force, acting on the ball. Okay. So here's our delta t. We just basically plug this into our standard velocity equation, v average, okay, and we find that our delta t is very small, 1.2 times 10 to the negative 3 seconds. And then we will find the net force. Okay, so the net force is going to be the change in momentum that we figured out divided by the time, the delta t, which is very small. And so for that time frame, we have 2,708 newtons. Another example, a car, 2,000 kilogram, hits a barrier at 20 meters per second, deflects off the wall at negative 4 meters per second. So we've already established our pluses and minuses. If the collision lasts for 0.120 seconds, find the impulse delivered to the car due to the collision. The magnitude and direction of the average force. So we need to find the magnitude and the direction of the average force exerted on the car. The impulse delivered to the car due to the collision is going to be equal using our impulse equation. But we're not going to use a force in here and a time. We don't, because this is equal to that and that is equal to that. We can work with those equations. So the first thing we need to do is to find the initial conditions, okay? And so the initial conditions of our momentum is going to be equal to 40,000 kilograms per meters per second. Our final conditions, it will be equal to negative 8,000 kilograms per meter per second. Notice that in the velocities, we have 20 meters per second going into the barrier and coming back out at negative 4.0 meters per second, changing direction. Okay, so the impulse is just a difference between the final and the initial momentum of the car. Because remember, impulse is equal to delta P, the change in momentum. And so plug in the values and we get a impulse which would be 48,000 Newton seconds, or it's also would be correct if you said kilograms times meters per second. The magnitude and direction of the average force exerted on the car. So let's find that. Well, we already know what the impulse is, or the change in momentum. We know the time. And so we just simply divide the time into that, and we get the average, or the impulse force, average force of 4 times 10 to the 5th newtons. So let's look at another example. A car, 3,000 kilogram car, hits a barrier at negative 40 meters per second, deflects off the wall at 10 meters per second. If the collision lasts for, and actually they're giving us a time, 0.240, find the impulse delivered to the car due to the collision. B, the magnitude and direction of the average force. So they want us to find the magnitude and also the direction of the average force exerted on the car. Okay, so first thing to do is take the momentum, the initial condition momentum, and figure that out. Then take the final. Okay, both of these will have different velocities. The masses will be the same, of course. And so we get our momentum, our initial momentum here. And we also get our final momentum right there. And as we did in the last problem, we subtract the final, or the change in momentum, from the final minus the initial, and we get our answer, the change in momentum, or this is the same as impulse, and you could have units of This is supposed to be an N. So Newton seconds. Okay. B, the magnitude and the direction of the average force exerted on the car. So again, what is the impulse? That's what we're looking for. The force, the magnitude and direction of the average force or the impulse force. Okay, we know what the change in momentum is and we know the time. So we have our average impulse force, or our average force, 6.25 times 10 to the 5th newtons. A lot of force happening in a very short time. Let's now change to the subject of the conservation of momentum, where the average force exerted by M2 on M1. So if we have a collision where M1, M2 are colliding together, basically the impulse force is going to be equal to the difference between these two right here. And so this force, each one of these blocks exert a force on one another as they collide. Okay, and we can see by this equation what that is. So let's look at a collision in one dimension. Now we have a couple different types of collisions. I'm going to talk just about collisions here in general. Okay, we have initial conditions and final conditions, and this what we're looking at right now. We're looking at initial conditions. We have two masses. We have directions. Okay, this could be a plus direction. This could be a negative direction. They may give you a velocity of, say, m2, but they may not tell you it's negative. You have to decide that. You have to decide how you're going to format your directions in your problem. So separate an initial final conditions, okay? So here we have the general equation. We have on this side the initial conditions. The mass, this is momentum plus momentum. Momentum of mass 1, momentum of mass 2 in the initial conditions, whatever velocity they're traveling at. And then over here we have the final. So we may be asked to solve for V1F and V2F, depending on the type of the problem, where we have two variables. So this is the conservation of momentum in an isolated system where both momentum and kinetic energy is conserved. Okay. So that means whatever kinetic energy goes into the system, it comes out, it's going to be the same in this type of collision right here. So let's talk more about collisions and the types of collisions that we will see. So we have what we call perfect inelastic and elastic collisions. Let's first look at perfect inelastic collisions. These types of collisions and kinetic energy is not conserved. So make sure you remember that. Inelastic collisions, kinetic energy is not conserved, but momentum is. And usually momentum is conserved in most all collisions. So our kinetic energy equation is going to be actually the change in kinetic energy, change in potential energy is going to be non-conservative work done. And this is going to be caused actually by deformation or changes that we cannot get back out of the system in terms of energy that has been used up by friction or heat. And in fact, most real-life collisions, we have mostly the inelastic type collision because we have some work done that is not conserved. And then we can break this up into our final and initial conditions of kinetic energy and potential energy, which we've talked in the last chapter 5. So let's look at the conservation of momentum equation. This equation is shown on the last slide. and we have the initial condition, and then we have a final condition. So this equation right here is what we actually are starting off with. We're going to have to derive an equation to solve this problem. Now we have mass 1 and mass 2 that are at a certain velocity and heading towards each other in a collision. When they do collide for the final, the two masses stick together and move as one off into a certain velocity. Okay. This is a typical inelastic equation. Always you have one velocity with two masses moving together. We call this a perfect inelastic collision because in most real life conditions, even though these are inelastic collisions, not all things will stick together. But in general, for our purposes, we will use the idea that they do stick together because there's only one velocity. Now, if there was, say, two cars that crashed, okay, they may stick together for a while and then separate, but that kind of crash is an inelastic collision. So going back to our conservation of energy momentum equation, we represent the final velocities with a prime. Looks like a hyphen. Okay, so on the right side of the equation, we have our final velocities. And we have our diagram showing before and after. Okay, and then what we're going to do is, because we are going to have only a single velocity, which will be these two masses, they will have V prime. We will actually lose the designation of V1 and V2 on the after. Okay, and so what we do is, to solve for that velocity, we use this equation. So this is the derived, or the equation used for inelastic collisions in general. Okay, let's look at another example. Two massive crates collide with one another. M1 being 100 kilograms, moving at 9 meters per second, collide with M2, 200 kilograms, traveling at -6 meters per second. Now notice in this case, they are giving you a negative sign, okay, because that's the only way that you would know that the two crates are heading together into each other in a collision. Find the direction, velocity of both crates. Okay, so let's do that. So here we have an inelastic collision set up. And also they want us to find what is the momentum. So this is the equation we use. This will give us the velocity, V prime, of these two going off in that direction. So plug in the values and we get negative 1.00 meters per second. Okay, and they want us to find the momentum, and that is going to be -3 kilograms meters per second. Now, even though in this particular situation it's going off this way, so we have to assume this is negative and this is the positive. Okay, because we have a negative answer that both masses are moving to the right at -1.00 meters per second. It could be the opposite way. It depends how you set the problems up, or how you're asked to do the problem. Let's look at example 6.5. A boulder with a mass of 2,500 kilograms slams into a second boulder at 85 meters per second. The second boulder runs into the first boulder with a speed of 105 meters per second. Both boulders collide and travel at a velocity of 93 meters per second. Well, they want you in this case, in A, what is the mass of the second boulder? So they want us to find what is the mass of M2? You have the two velocities, and here you have where they're going to stick together and they're going to move out as one velocity. So what is the mass of the second boulder? Okay, so here is our derived equation, inelastic equation, perfect inelastic equation. And so what do we got to do? We just have to solve for M2. We have M2 in the bottom, we have M2 in the top, and then this is our equation that gives us a solution to M2. And we find the mass of the second boulder to be 1,667 kilograms. What is the momentum of both boulders after impact? Well, we must remember now both boulders are sticking together and traveling at one velocity. Okay, so we need to add those up, sum the masses times that velocity, and we get our momentum. Now let's move on to elastic collisions. Elastic collisions are similar to inelastic collisions, but there is one difference. When these objects collide, kinetic energy is conserved. Momentum is also conserved. Now, momentum is also conserved on the last example, inelastic collisions. Kinetic energy was not conserved. But in an elastic collision, kinetic energy is conserved. All the energy going in for elastic collision equally comes out. Objects do not stick together, but rather deflect in different directions. So you can think of like a ball bearing, steel ball bearing. If you bounce two ball bearings off of each other, they actually, basically the energy that was put into them in the collision comes out almost 100%. So let's take a look at, again, using two boxes. And we can see that after the collision, this is before, this is after, okay. And so we see that each mass, M1 and M2, are going to go off in different directions. Okay, so where we have V1, we can say V1 initial, and this is V2 initial. This is V1 prime equals V1F. This is just nomenclature to understand that we are going to use the prime right here for the final. Okay, some books may just use the final. We're going to use the prime. So this is definitely the conservation of momentum. And this is the equation. So in this equation, you're going to have to find two variables, V1 prime and V2 prime. So let's look at an example. Two objects are on a collision in a one-dimensional isolated system. Mass 1 is 25 kilograms and traveling to the right, and at 25 meters per second. Object 2 has a mass of 45 kilograms and is traveling toward the left. And they're telling you the left, and they're also giving you the negative sign that you know. So we have this condition right here. They gave us our velocities, and they've given our mass. What we don't know, we know the mass is after the collision. This is before, and over here this is after. But we don't know these. We don't know what the primes are. And these are after the collision. So when solving two variables, we must derive two equations. Okay. Now, so to solve for V1 prime and V2 prime, in this equation right here, we have, and basically what this is just saying basically is that we're using the prime. We're not going to use these right here. Okay. And the same thing with the initial conditions. We're not going to use the letter I's and the letter F's. We're going to use this. So we have V prime 1, V prime 2, V1, V2. These right here are after, these are before. try to solve the two equations, unknown velocities, v1, vf. Okay, so I've done this for you. You should go back to your algebra book and see how to solve two variables. But right here, because this diagram did use the f and the I, these are the same thing as v1 prime and v2 prime. Okay, and by plugging in the values, you can solve for these two variables. Okay, and so this is basically solving for v1 in this example was negative 32.9. V2 prime was 12.1, both meters per second. Both kinetic and energy momentum are conserved in this collision. So all we did was take these two equations and solve for the two different velocities. And here's a description of after. V prime 1 was going to the left at negative 32.9 meters per second, and M2 was going to the right. We use positive 12.1 meters per second. Let's look at one more example. Two objects are in a collision in a one-dimensional isolated system, mass 1, and given our mass 1 is 42, and also traveling at a certain speed, 25 meters per second. And object 2 has a mass of 12 kilograms. It's traveling toward the right at negative 55 meters per second. So here we have all the information we need. We have the two masses and we have the two velocities, okay? Now, in this problem, let's take a look at very closely what the directions are. Mass 1, 42 kilograms, traveling to the left. Okay. So mass 42, this is right here, it's traveling to the left. Okay. And object 2 has a mass of 12 kilograms and is traveling to the right. So this mass right here is traveling to the right. They don't give us, sometimes they will not give you a plus or negative sign. You'll have to decide that by carefully reading the question. Again, we'll use this equation to solve for both variables, and our answers are right here. So what happens to V1, or actually M1, is that it changes direction. Now it's going the opposite direction at 10.6 meters per second, and V2 was traveling at 55 meters per second, and now it's going in the same direction that it was. I'm sorry, it was going in the same direction that it was, but now it's increased in speed to 69.4 meters per second.